morning. In the last lecture, we considered, based on the heat loss from a particular volume of the explosive and the heat which is getting generated within the explosive, we were able to define something like an ignition temperature. We defined something which we called as an auto ignition temperature, which we also termed it as the critical temperature. These things were based on, you have a certain volume of the explosive, some heat is lost from the explosive, we determined the heat loss, we also determined the heat which is generated within, and based on these things we had on the plot of heat, rate of heat, whether it is generated, whether it is lost. Under some conditions we could have a stable point and ignition temperature over here, and when the heat loss curve happened to be tangent to this, we called this as point C or this temperature as critical temperature. Mind you, the x axis was the temperature, the y axis was heat release, the white curve here was heat generated QC dot, and this curve was the heat which is lost to the surrounding, rate of heat loss. Now, we had got an expression for Tc, and the expression was, we had the auto ignition temperature or critical temperature minus the ambient temperature divided by the ambient temperature was equal to, we had the expression activation energy divided, I am sorry, it should have been the activation energy came in the denominator, we had the universal gas constant into the ambient temperature divided by the activation energy over here. Therefore, today we will try to get some more physics of this auto ignition temperature or critical temperature. We also said Tc minus T ambient, like for instance, had the heat release curve been extrapolated, we would have got the ambient temperature at which if the temperature of the explosive was same as ambient temperature, we said, well, this is the value of the ambient temperature, and initially the explosive could be at ambient temperature. The heat required to go from T ambient to this, we called it as preheat, or the temperature Tc minus T ambient we called as the preheat temperature. Therefore, we will also try to take a look at this preheat temperature and how the auto ignition temperature varies. Let us first take a look at the preheat temperature, namely the temperature of preheat, namely Tc minus T ambient. I can now write it as equal to R naught into T ambient square. I just take the T ambient on top and I put it as activation energy over here. I am interested in determining the magnitude of this. Let us do for a specific case. We always say that, well, the activation energy of an explosive is quite high. Let us take a value of EA equal to 100,000 joules per mole. Anyway, the value of the universal gas constant R naught is equal to 8.314 joule per mole Kelvin, and we now take the ambient temperature as equal to, let us say, 25 degrees centigrade, which is equal to 25 plus 273, which is equal to 298 Kelvin. First of all, before doing that, we should also check whether this equation is homogeneous. That means it has same dimensions on the left hand side. Left hand side is unit of temperature. Well, EA is joules per mole, R naught is joules per mole Kelvin. This is 1 over temperature. Well, right hand side also temperature. Therefore, this equation has the same dimensions. Let us now plug it in. The value of Tc minus T ambient therefore works out to be 8.314 multiplied by T, that is 298 square, divided by the value of activation energy. We said it is equal to 100,000 joules per mole, and when I calculate this value, it comes out to be something like 7.4. That means the change in temperature between the auto ignition to the ambient is something like 7.4 degrees centigrade. Well, this is a small number. That means the preheating required, the heating required to go from here to here is a small number, and that is a cause for concern. That means, if I have an explosive gas mixture such as here, and if I allow some preheating to take place by a small amount, well, it could go into an explosion, or it could automatically spontaneously auto ignite. Therefore, but this is something which poses some problems, and if we go back to the examples which we took, like for instance, let me cite one or two examples. If you go and see the example of, let us say, the Texas City disaster, and what was in this particular accidental explosion? We had lot of this ammonium nitrate things being piled, the cartons of ammonium nitrate being stacked one on top of the other, and it was something like 7,700 tons. This was all within the hull of a ship, and the hull of a ship is insulated, it does not allow heat to leak through, and therefore, it is in an environment in which it is not losing much heat. And if by chance any chemical reaction at any time, like we say omega is equal to dC by dt, like dC by dt, that is rate of change of concentration with respect to time, we had written it as a c to the power n into exponential of minus E a by R 0 t. At any temperature there is some incipient chemical reaction taking place, and if by chance some small temperature increase happens, well, it could just explode, or it just cumulatively react, and so such a high temperature takes place that a thermal explosion can take place, and this is what happened in the Texas City disaster. Well, in the example of the Bhopal gas tragedy, if you take, what happened? We told in terms of tanks containing methyl isocyanide being stored, and we also told maybe because of the conditions of like a faulty valve which was there and not properly hooded, some water leaked in and some chemical reaction started. But mind you, if the system was all right, what we should have had? We should have had a refrigeration coil which would still keep the methyl isocyanate cool, and somehow it was not working, and that is how we got the reaction to take place, temperature built up, the higher temperature caused the rate of reaction to go up, and this cumulative type of a reaction which keeps on increasing with the increase in temperature is what caused caused the leakage or a high pressure and the leakage of methyl isocyanide, the isocyanide liquid and vapor got leaked, and that is what affected the people. Therefore, you find that yes, we have to keep the preheat to a low temperature, and maybe what is the procedure is, maybe you should increase the heat loss from the system. Therefore, now we ask ourselves one question, see, we are telling, well, the temperature Tc, the ignition temperature Tb, and also the stable temperature Ta depend on heat generation Q dot C, so much kilojoules per second, and also the heat loss from the system, namely QH dot, which is also in kilojoules per second. It is the competition between these two which gives me my critical temperature, that is the auto ignition temperature and the ignition temperature. But is it really so? Let us put this figure again, because we need to be clear about this. We talk in terms of generally Q dot, kilojoules per second, we talk of temperature. We say, well, the heat loss rate is given by this, we call it as Q dot H over here. This is the ambient temperature at which, well, the heat loss from the explosive to the ambient is 0. Now, below this temperature, well, the explosive receives heat from the ambient. For the condition of auto ignition, you have the heat release curve, which I show by dotted line over here, something like Q dot C, and this is my point Tc. If I had something like an ignition temperature I am looking at, maybe I would be looking at something like this over here, this dotted line. This is my ignition temperature Tb, but let us focus first on the auto ignition temperature, that is the critical temperature Tc over here. Now, this Tc is when the heat release, that is Q dot C, is same as QH, and we also said the two conditions are it is equal and the line is tangent to this particular curve QC. That means auto ignition temperature really depends on, let us say Tc should be a function of QC dot and also the heat loss to the surroundings. Therefore, the auto ignition temperature, if I supposing I want to measure the auto ignition temperature of, let us say, hydrogen with oxygen or hydrogen with air. Therefore, if I want to do this, well, if I have a casing in which this particular explosive is contained, is something made of SS, and this is the structure in which the gas is contained over here. And in one case it is made of stainless steel, which allows some amount of leakage of hydrogen. In the other case, I have it made out of some material and in some other geometry, such that it does not allow the heat to go through. Well, the auto ignition temperature in these two cases will be different. It is a system problem, because it decides on the heat generated and how the casing allows the heat to get transferred. Therefore, it is a system problem. Therefore, but if I look at the literature, I get values of auto ignition temperature which is given. Let us take a look at some values which are given in literature. We find that yes, we can have for methane, the auto ignition temperature is given as 540 degrees centigrade. If I go to ethane, methane is CH4, this is C2H6, the value is 515 degrees centigrade. Let us put some 3 or 4 down and discuss why, how they are able to specify this. In the first place, if it is a system level problem, depending on the type of system, well, the auto ignition temperature should change. Propane is 450 degrees centigrade. If I take kerosene, now I go to a large molecular mass substance, kerosene, again in the same alkane structure, it is equal to 210 degrees centigrade, and I take the last one, maybe hydrogen. The auto ignition temperature is given in literature as something like 406 degrees centigrade. How is it that the auto ignition temperature is given as a property of the fuel? Mind you, this is mixed with air, air, air. We are not talking of anything about heat loss or the system under which the auto ignition temperature is measured. Is it really right? Are there some reasons? Well, the reason is, whenever we talk of these substances, we talk of all explosives, as we keep telling, are substances which have large values of activation energy. That is, the value of activation energy EA, we said, is typically between 80,000 to something like 160,000 joule per mole. When the activation energy is high, what is the implication? Let us see the implication. If I were to make a plot versus, let us say, temperature over here, and let us say I have Q dot C over here, what is going to happen? Well, at the ambient temperature, low temperature, the value, let us put down the value of omega. Omega is equal to the rate of a reaction is equal to A concentration N exponential minus EA by RT. If I look therefore at QC dot, Q dot C, the rate at which heat is getting generated, which I want to plot over here, kg per second, well, it is equal to omega into, that is so much moles per cc second into volume moles per cc into the heat which is generated per mole, and therefore, QC dot is equal to A Cn into exponential of minus, mind you, it is universal gas constant R naught minus EA by R naught T over here. And we found that for large values of activation energy, it goes slowly initially with time and temperature, that is both can be represented on this axis, because as time increases, temperature also increases. Therefore, as a function of temperature, if I were to plot this, well, initially the temperature increases rather slowly because of the large value of this, and after some time, well, it goes off exponentially. When the value of EA becomes sizable, corresponding to R naught T becomes sizable with EA, well, it goes off. And therefore, what is happening is you have a period in which there is hardly any temperature increase, and after some time, which corresponds to the critical value or the auto ignition value, and that is where it takes off, and this is what we said is preheat. That is, during the preheat process, what really happens is there is a small perceptible increase in the temperature, and that causes the reaction to proceed faster, and after the preheat stage is over, well, the reaction goes fast, and this is why what happens is the actual heat is liberated in this particular phase. And mind you, we did this total problem also, we said it reaches a maximum when there is still some concentration left, and therefore, thereafter it drops down like this, and this is when the total temperature, total reaction is over and the maximum temperature is reached. After this, there is hardly any change in temperature, and therefore, what is it we find? Well, you have a period in which heat is getting released after a certain amount of preheat, and during preheat some chemical reactions occur. It is something like an induction time, a time during which the reactions occur and make sure that the quantities of the chains which are required to make the reaction go fast are ready, and once that is ready, well, it goes into this, or rather I can now replot this reaction as saying, well, my QC dot as a function of temperature is almost something like in some phase the temperature is not changing at all. I will go through it tomorrow or in the next lecture, and then after some time, well, I have a step increase, and this corresponds to the rapidly increasing phase. Therefore, this is the duration of the chemical reaction, and since the chemical reaction occurs over a much shorter period, well, this is the chemical reaction time. Since the chemical reaction time takes place, well, this is the period, maybe I will just therefore say this is the period from here to something like this is the chemical reaction period. Since this is much shorter than this, what is happening during this short period of time, there is not much time for the heat to get rejected, and therefore, the heat transfer really does not play a role because this is occurring very fast, and therefore, the question of heat transfer does not really affect my Tc when the value of the activation energy is large. And for these substances, we do find, well, the activation energy is large, and therefore, these explosives, that means methane with air, ethane with air, propane, kerosene vapor with air and hydrogen with air, are things which have a large value of activation energy. So, also the condensed explosives, liquid explosives which we talk of, and therefore, we say, well, under these conditions Tc, that is the auto ignition temperature, is sort of a function of the explosive only, that is the chemistry of the explosive alone, and does not and is not a system dependent parameter. By system dependent parameter, I mean under all conditions of experiments, well, the heat loss from the system or the type of wall of the system does not really affect my auto ignition temperature. Therefore, this is what we learn about auto ignition temperature, and therefore, it is still possible to decide the auto ignition temperature as a function of the chemistry of the explosive. What we find from this table is methane has a simple structure. As the structure becomes more and more complicated or more and more involved, the auto ignition temperature drops until for kerosene it is dodecane, that means I am talking of C12 into H26. Well, the auto ignition temperature has decreased. We find as the structure becomes more complex, it ignites a little bit easier, but it also depends on the structure of the substance, like for instance, H being a structure H2 over here has a much higher value than many of these alkanes over here. Like this, in literature you have values of auto ignition temperature, and they are not a function of the containment or the structure or the system they are in, just because it so happens that the activation energy is a large number. Well, this is all about the auto ignition temperature, the ignition temperatures, the same thing holds good. But since we talked of the time of the chemical reaction, can I put this down in terms of chemical, can I get an expression for the time for chemical reaction? Can I get a value like let us say Tc, can I derive an expression for Tc and discuss further? See, because when we talk of preheat, which corresponds to the induction time, let us call the induction time as Td. Whenever we talk of a large value of activation energy, well, I have a long induction time followed by a small value of chemical reaction time. Let us first get an expression for Tc, and then we will later on take a look at the induction time. If we take the time for a chemical reaction, well, I can tell myself Chemical reaction liberates heat. And why does it liberate heat? The initial concentration from C naught, it falls to a value of 0 at the end of the reaction. Therefore, I can tell myself, well, the time for a chemical reaction, after all I am interested in time, that means I have initial concentration divided by the mean value of the rate of reaction, let us say omega, mean value. Rather, I can put this down as equal to C naught, which is the initial concentration, divided by dC by dt. Let us not look at the sign, we just say, well, the value of dC by dt, C naught has units of mole per cc, this has units of mole per cc second, and therefore, the unit of initial concentration divided by the mean reaction rate comes out to be second, and that is the chemical reaction time. Can I get a value for this? If I were to get a value for this, I must also say, well, my omega, which we just discussed, we said is equal to A Cn exponential of minus Ea by R0 T. Well, the temperature is continually changing, and what is the change in temperature we see? Well, to begin with, well, with respect to time, the temperature starts at T0, it starts slowly, after some time when the preheat is over, it jumps up, and then, well, the temperature steadies out and you reach a maximum value. Therefore, we find that till the time the critical condition is reached, that means the temperature is Tc, there is hardly any reaction, and chemical reaction starts here at a high value. Therefore, when I refer to the mean value, maybe I should be taking off in terms of the Tc value, and therefore, I can write the value of the chemical reaction time or the Tc as equal to C naught divided by, I say, A into concentration N into exponential of the value of minus Ea by R0 into Tc, and this gives me my mean chemical reaction time. Well, we talk of time for chemical reaction. We must also remember, yes, while evaluating the autoignition temperature, well, we find that the chemical reactions are not important as long as the activation energies are large. But in an ordinary situation, well, the balance between the chemical time and the heat loss time, or we must consider the heat loss also. Can I have something like a time or a characteristic time for heat loss? Let's take a look at this. The question I am telling is, see, we talked in terms of heat generation. We say, well, heat generation initially is very slow and thereafter it picks up, and we are talking of a heat generation time which is characterized by the heat time for chemical reactions Tc. Supposing we are talking of heat loss, can I also have a characteristic time associated with heat loss, or let us say heat transfer? What is the time associated with heat transfer? Let us say I have heat H, therefore, I say what is my characteristic heat transfer time? Can I determine it? To be able to do that, let us take a look. Yes, I have a volume of explosive, let us say volume. We are again locked in this particular assumption of this volume containing the explosive gas mixture. We say, well, it is a lumped mass system. The properties are uniformly same throughout this particular volume over here. Let the temperature initially be, let us say, hot. I am just not looking at chemical reactions, I am interested in heat transfer. I say let the temperature initially be Th over here, let the volume be V meter cubed or V over here, let the substance be of density rho, rho is uniform throughout, and this lumped mass, let us say, is rejecting a certain amount of heat Q dot H to the surroundings, that means it is losing some heat. To be able to lose heat, well, the ambient temperature T ambient must be lower than Th, that means Th is greater than T ambient. Can I get an expression for QH? Yes, we have been doing this, and what did we do? We had the boundary. At the boundary we said let the surface area of the boundary be S over here. let the heat transfer coefficient at this surface be small h, so much watts per meter square Kelvin, and therefore, what is the rate at which heat is getting lost from the surroundings to the surroundings? Q dot H is equal to the area into the heat transfer coefficient, or I should rather put heat transfer coefficient into the surface area into we say T H minus T ambient is the total heat which is getting lost. Therefore, at any point, let us say the initial temperature is T H, let us assume at any time T, that means at T is equal to 0 the temperature is T H, at any time T let the temperature of this lumped volume be T. Why is that? Because it is losing heat, the temperature is falling, therefore, we say well the heat loss when the temperature T within the body is T, the ambient temperature is T ambient, because the ambient temperature remains same because it is something like a reservoir, its temperature does not change, is equal to so much joules per second, which is equal to watts over here, so much watts. See, I am interested in a time element, I am interested in how the temperature inside this body is changing, and based on the change, just like we had a heat release curve, I was able to define something like a chemical reaction time. I want to determine a heat transfer time. How do I do this? If I look at the value of the heat which is lost, why is it is losing heat? I have a certain mass over here, a thermal mass whose temperature is changing, and therefore, if I look at this, well the mass of this particular volume is equal to rho v is the mass. If the specific heat of this is a constant volume, let the specific heat be C v, so much joules per kilogram Kelvin. Therefore, I say well rho v C v is the thermal mass over here, mind you the thermal mass in terms of mass into specific heat. And what is the rate at which the temperature is changing? Well, it changes by let us say a small value dt delta t in a small time delta t over here, which if the time elements are small, I can call it as dt by dt, that is d capital T by small t. Well, it is losing heat, this is negative, therefore, I have minus rho v C v dt, and this must be the value of Q h. Therefore, Q h I can write it as again equal to H s into T minus T ambient, this is the rate at which it is losing heat, and therefore, now I can write this expression as dt by T minus T ambient is equal to minus, I bring the minus over on this side, I have minus H s over rho v into C v. This is the thermal mass of this particular system, and H is the heat transfer coefficient at the surface, S is the surface area through which heat is getting transferred outside, I have dt by this. Now, I want to find out what is the net value or net change in temperature corresponding to this. Well, I had dt by dt here, therefore, I should have had a dt over here. Well, this is my expression in the differential form. Well, to be able to calculate the time required for the heat to be transferred, that means let us find out the time taken. Let us put that down. We are interested in finding out the time taken for the heat which is getting generated, that is let us say time taken for the temperature to drop from a value T h to T. That means, time T which is taken, or let us say T taken for temperature to drop from T h to T. Therefore, I just integrate this expression from let us say dt by T minus T ambient. I integrate it from the initial value h from the hot value to any temperature T h, let us say T capital H is the initial value, and what does it correspond to? It is equal to the time taken on the right hand side is equal to minus H s divided by rho v C v into dt over here. When I integrate this expression, that means I go from the high temperature to the low temperature, and it is losing heat, I go from 0 to T over here, and therefore, what is it I get? I get, well, this is ln form, therefore, I get ln of T minus T ambient, that means T, that is ln of T by T infinity, the limits of integration are from Th to T, therefore, ln T minus T infinity divided by Th minus T infinity is equal to minus, that means ambient temperature over here, minus Hs divided by rho v Cv into the time over here. Or rather, if I were to put it in explicitly in terms of this, I can write T minus T ambient divided by Th minus T ambient, take exponential on both sides, I get e to the power minus Hs divided by rho v Cv into time over here. Let us try to plot it, let us try to discuss it. What is my characteristic heat transfer time? Well, this is what we say is the Newton's law for cooling. Any body which is hot, when it is radiating out, it follows this particular law as exponential to the power minus Hs by rho v Cvt, where rho v is the mass, this is the specific heat into the time. Well, let us try to plot this out and see whether we can infer something on the characteristic heat transfer time. We plot that value, let us see, the initial temperature was, let us say, hot temperature, this is my temperature axis, the initial value is Th over here. Well, the ambient temperature is T ambient. What is this? What does this expression tell us? At any time t, the temperature is T minus T ambient, and if I want the final temperature to be equal to ambient temperature, I get 0 here, or that will happen only after infinite time, or rather if I can get the final expression, reach the final value, this is the time axis over here, rather I start over here and it keeps on going and it takes infinite time to reach the ambient value. At any intermediate value t at which I am interested in, at any value t, well, the temperature is T over here. But then according to this, it is a gradually decreasing value and it never really reaches the ambient value, it takes infinite time. It is almost impossible to have something like a characteristic heat transfer time. And there is no point in telling, well, the heat transfer takes infinite time, by which I cannot really make much sense out of it. But one thing we also see, in this particular expression we see, since it is exponential, the major changes take place in the initial phase, and after some time, well, the changes are very small. If that is so, can I still use this figure and write, well, can I write a characteristic heat transfer time? Mind you, I am not able to clearly perceive a heat transfer time from this particular curve. But since the major changes are occurring in the initial phase, well, I say the initial value or initial value of the heat in the body compared to the ambient is Th minus T ambient. At any time we say it is equal to T minus T ambient, we tell ourselves, well, it is gradually falling fast initially. Therefore, if I say T minus T ambient is equal to 1 over E, 1 over exponential of, let us say, Th minus T ambient, that means since it is exponential, what is happening? See, exponential curve, if I say the value of E, what is E? Is that Neperian value, that is, we say log to the power E, that is the Neperian base E, and E is equal to, we say 1 over 1 plus 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial and so on. What does E say? It sees something like it takes care of the cumulative effects, and therefore, if you take the cumulative effects and you say, well, based on the initial value, which is this, well, I say when the value is 1 over E of this, well, this could be my characteristic heat transfer time, because beyond it the values are changing rather slowly. Therefore, I tell myself, well, I define the heat transfer time as the time required for the value to fall to 1 over E of the original value, and therefore, I tell well in this particular expression now I can put this value down. I say well it is an exponential decrease, and therefore, I write when T minus T ambient divided by Th minus T ambient is equal to 1 over E value, then I say well my characteristic time is equal to the heat transfer time, and therefore, let us work out the time based on this particular expression. Therefore, now I say T minus T ambient divided by Th minus T ambient is 1 over E. Therefore, I say 1 over E is equal to, on the right hand side here I have e to the power minus h s by rho v C v t, that means e to the power minus h s divided by rho v into C v. This becomes my characteristic heat transfer time, because I presume that this is the time during which the maximum heat transfer takes place, afterwards is going slowly, and therefore, on this left hand side I have e to the power minus 1 is equal to e to the power minus, therefore, minus 1 is equal to this value. Let us put it down and see what we get. Therefore, now we will get a value say minus 1 is equal to minus H s divided by rho v C v into T h over here, that is the characteristic heat transfer time. Minus and minus get cancelled and I get T h is equal to rho v C v divided by h into s over here. Let us ensure that the dimensions are all right. Rho has units of kilogram per meter cube, volume is so much meter cube, specific heat unit is joule per kilogram Kelvin divided by what is it we get, the unit of H, let us just put it down over here. The unit of H is joule per second watts per meter square Kelvin, and S is meter square, the surface area. Therefore, what is it I get, meter square gets cancelled, Kelvin and Kelvin gets cancelled over here, kilogram gets cancelled, meter square gets cancelled, joule gets cancelled, we are left with time, and this is second. Therefore, Th in seconds is the ratio of the thermal mass of the system rho v C v divided by the product of the heat transfer coefficient into the surface area through which it is rejecting heat. Therefore, now we are able to get a characteristic heat transfer time, and let us see whether I can make some sense out of all this, whether I can relate the characteristic heat transfer time with the characteristic chemical reaction time. Rather, I am looking at an expression between T c and T h over here. Is it possible? Before doing that, let's discuss what is the role of these times, whether they may have something to do in the case of an explosion, and therefore, let me broaden the discussions at this point in time. We tell ourselves, well, I have been able to calculate the heat transfer time. Let's put it down. I say, well, Th is equal to rho v C v divided by H s. You know, many people also call the heat transfer time in terms of maybe the thermal response of a system. Why is it? If I take a look at the expression, I have T minus T ambient divided by Th minus T ambient, that is the initial value is Th over here. We had it equal to e to the power minus H s divided by rho C v into something like rho C v into V, or rather I should have put it as rho V C v into the time over here. If now I were to put this characteristic time over here, I get is equal to e to the power T over the characteristic heat transfer time, and this is sometimes known as the response time of your particular body. We say, well, the body is hot, it takes a time Th to respond, and we get e to the power minus T by Th is the dimensionless ratio of the excess heat compared to the ambient in the denominator divided by the excess heat at any particular time over here. Therefore, this is also talked in terms of the thermal response time. Whereas, when we talked of the chemical reaction time, what did we tell? Yes, chemical reaction time is the initial concentration divided by the rate of chemical reactions at when the temperature T is equal to the critical temperature over here. Now, I want to examine whether there is some relation between TH and TC, for which we wanted to discuss a little bit more and see whether there is some relation. Let me consider the following cases. Let me consider the following. Let us say I have a substance over here, an explosive substance, an energetic substance. Well, the substance in the given medium or in the particular system in which it is contained has a characteristic heat transfer time Th. If the characteristic chemical reaction time of the substance is Tc, and if we say, well, Tc is very much greater than Th, what is the implication? In other words, all what we are saying is, well, Tc is larger than this. Therefore, if I say some heat is getting generated, then I say, well, the heat is getting generated over a large time. That means, the value of Q dot C is going to be very much less. That means, the time for heat generation is large, therefore, the rate of heat generation is small, Q dot is small. But since the heat transfer time is now much smaller than the chemical reaction time, the rate at which heat is getting lost, that means Q dot H is large. That means, before some significant amount of heat, that means heat is getting generated, heat is also getting lost. Since the time of the chemical reactions Tc is large, even before some heat is getting generated, since the time of this heat transfer is much smaller than Tc, well, it gets dissipated into the medium and the explosive can never really sort of go into the cycle of increasing temperatures and have chemical reactions which generate more and more products, and therefore, it explodes. The explosive cannot really explode. While if the chemical reaction time is smaller than the heat transfer time, well, what happens? During the short time itself, the chemical reactions take place, heat gets generated, therefore, Qc is very large, whereas since the heat transfer time in this case is large, you know what is happening? It is not able to transfer out the heat which is getting generated, and that was the condition we observed. You know, when we have a spike in the reactions, the rate is so fast, and whatever be the time is quite large compared to this, and therefore, the amount of heat which is conducted away or which is sent away is much smaller, and therefore, heat begins to accumulate here. Because of the heat accumulation, the temperature further increases and it goes into a cycle, and all of a sudden you have a spurt in the energy release, and therefore, this condition of Tc being very much less than Th will be a condition for an explosion to occur. I think I should repeat this in a slightly different language. What have we said so far? An explosion occurs when the activation energy is large. In other words, all what we are saying is an explosion takes place when the rate of heat release is such that we say Q dot as a function of time is such that initially nothing really much happens. All of a sudden there is a spurt in the rate of the reaction, lot of heat is generated, and you have an explosion taking place here. That means, the energy release takes place over a very small time. But along with this, we also now see, if I were to now say, well, my chemical reaction time is such that I enclose it in a system in which my heat transfer time is much larger, that means Tc is less than this. The time for heat transfer is such that it takes longer time for the heat to get transferred out. Therefore, there is accumulation of heat during this short time. Well, the system which is there keeps on increasing in temperature and it sort of explodes. That is one. Second is, well, therefore, we say the activation energy being large indirectly gives us the condition that Tc is very much greater than Th. Therefore, let us work on this. Let us see what is the relation we get between Th and Tc, and it comes out that we will be able to catalog an explosive based on this particular ratio, and this ratio Th by Tc, we said, well, heat transfer time must be larger than the chemical reaction time, is told the ratio Th by Tc is known as Dahm-Kohler number. And for an explosion to occur, the value of the Dahm-Kohler number must be large. That means the characteristic heat loss time must be very much greater than the chemical reaction time. Let us try to use this, let us try to see whether we can get the expression for the type of explosive which will undergo an explosion based on these two times. Since we have determined these two times, it should be possible for us to put it together. Let us say I am interested in the ratio of Th by Tc. Well, I say, well, I have just now calculated the value of Th, and what was it? It was equal to rho v into Cv divided by Hs, so many seconds. What was the value of Ts? Tc? Well, Tc also I know, it is the initial concentration C naught divided by the reaction rate, and at what temperature do we say? Well, we take it at the critical temperature, that means A Cn, that is omega A Cn into exponential of minus Ea by R naught into Tc. I want to get the expression for this. Can I simplify this in some way? Can I get, now it is quite difficult to solve this. I have an exponential term, I have Tc here, I have all these properties over here. Can I solve it and get the expression for Th by Tc based on which I make some recommendations? Therefore, let us try to solve it. We also recognize when we talked in terms of the energy loss and energy gain, that means we had q dot over here, which could have been qh and let us say qc, q dot c and q dot h as a function of temperature. What did we say? Well, the qc curve was something like this, q dot c curve, and the qh curve was a straight line. This was the point C we had, this was T ambient over here. And how did we determine Tc, the value at Tc and or the value for the condition C? We said that the magnitude of qc dot is equal to the magnitude of qh dot 0.1. Second is the qh curve is tangent to the qc curve at point C. Therefore, let us look at the tangency condition and see whether I can simplify this expression. We will go to the other side of the board and try to solve this. Well, we have the expression d by dt, that is the tangent, because the x axis is time axis, A Cn exponential minus Ea by R0 t, that is we are looking at tangency condition at t is equal to Tc. We also found that this is equal to so much moles per cc second. Therefore, I had to multiply it by V to get moles per second. I had also to multiply it by Q to be able to convert. That means, I had so much joules per mole, that was the value of V over here. Therefore, we had ACN exponential minus Ea by R02 into V into Q, and this was equal to the value being tangent over here. The heat loss was equal to Hs into T minus T ambient. Let us change the bracket to a curly bracket over here. This was the condition. Let us solve for this. What is it we get? This is under T is equal to Tc. Therefore, I can write it as ACN into exponential minus EA by R0 Tc at t is equal to Tc. Differentiate this, I get E0 minus and minus E0 by R0 t, this becomes minus t square, therefore, minus and minus get cancelled over here, E0 RT square into V into Q is equal to, this differentiated gave us Hs because T ambient is a constant, and therefore, I had the expression ACN exponential of minus EA by R naught Tc is equal to, I get is equal to Hs divided by E0, I am sorry, it should have been activation energy EA divided by R naught into, well, I am evaluating it under condition Tc square over here. That means, this should have been Tc because I am evaluating it at the critical condition T is equal to Tc into Vq. Well, this gives me the expression for ACN exponential minus EA by RTC, which is in the denominator over here. Therefore, I can write this expression as, let's use this part of the board to write the final expression. I get the value of Th by Tc as equal to rho V Cv divided by Hs divided by, now I get C naught divided by the value what I get here again Hs divided by EA activation energy into V into Q divided by R naught into Tc square. I want to simplify this, and therefore, I note, well, Hs should have go on the numerator and this gets cancelled. I also get, well, the volume and volume get cancelled because this comes in the denominator, this goes in the numerator. Therefore, I get Th by Tc as equal to rho V divided by rho V has already got cancelled, rho V gets cancelled with V over here. I get rho Cv divided by C0, rho Cv by C0 into the value of R naught into Tc square divided by EA into Q. Let us check this. Th by Tc is equal to rho Cv divided by C naught into R naught into Tc squared goes on top into activation energy into the heat release per mole. Let us see whether I can simplify some of these things. You know, if I talk in terms of the thermal mass and if I talk in terms of the initial concentration, well, I am talking in terms of maybe kilogram per meter cube. I am talking in terms of Cv, so much joules per kilogram Kelvin. I am also talking in terms of moles here, let us say moles so much centimeter cubed or meter cubed. I am talking in terms of moles per meter cube. Therefore, you know, this expression tells me it is something like kilogram and kilogram gets cancelled over here. I am talking meter cube gets cancelled. This is something like joules per mole into Kelvin. That means, we are talking of specific heat per mole, and we can say this is equal to Cv bar, wherein we are talking in terms of so much kilojoules or joules per mole Kelvin, which is equal to the specific heat in per mole, and therefore, I can write this as equal to Cv dash, which is instead of taking in terms of joules per kilogram Kelvin, I am considering joules per mole Kelvin, and therefore, I get the value as Th by Tc is equal to the specific heat into, let us say Tc, I bring one Tc here divided by Q over here, and then I am left with R naught Tc by EA, that is activation energy into Q. Well, this becomes my expression for Th by Tc. Let us try to see whether I can make some sense out of it. Can I put it in some other form? Can I use the things which I have studied already to be able to interpret it? First of all, I would like to say, well, we have already learned that Tc minus T ambient, which is the preheat value, is a small number, and we said Tc by minus T ambient divided by T ambient, that means I should have put it as T ambient over here, T ambient over here, is equal to R naught T ambient divided by we had A activation energy over here, which was a large number, and this was very small, and therefore, we said when the activation energy is very large, well, Tc is almost equal to T ambient, and therefore, I can simplify this expression and write it, because we are interested in trends, we are not working out a numeral, and therefore, I can tell, well, the value of Th by Tc is equal to, I have the specific heat in joules per mole Kelvin into T ambient divided by the value of Q, so much joules per mole what is getting generated, into I have R naught into T ambient divided by E A is what we are getting. See, here I have taken Q twice, I should have taken Q once, maybe since I took Q over here, it should have just been over here E A. Therefore, I have taken Q here and here, which was not correct, Q is only over here. Therefore, this is the final expression what I get. And what does this tell me? Well, here you are looking at, if I look at the value of Q by Cv into T infinity, we are talking about the heat generated, whereas we are talking of the initial heat which is available to you. Here we are looking at the activation energy effects. Therefore, since we are looking at this divided by this, let us put it in terms of Tc by Th, we say is equal to Q divided by Cv into T infinity multiplied by Ea divided by R naught into T infinity. Therefore, you see that this is a dimensionless number, joules per mole, we are talking of the energy released per mole divided by the initial energy, which is a non-dimensional number, which tells me what is the magnitude, how much heat is getting generated. If I take a look at Ea by R naught T infinity, all what it tells me is what is the spiking which results. We told ourselves as Ea increases, well, if Ea is large, I have, let's put that down. This is basic to our discussions. Therefore, we say if I were to look at the progress of the chemical heat generation, well, when Ea is small, I have this. When Ea is large, well, it goes like this. When Ea is still larger, it goes like this. Therefore, as activation energy goes, the spiking or the rate of heat generation spikes up. Therefore, this is a spiking non-dimensional term for heat release, spiking of heat release, whereas this tells me how much heat is getting generated. We also see if the value of the ambient temperature is high, then what is happening is if the ambient temperature is high, the amount of heat which or the amount of spiking what we have cannot be very large, because the temperature goes up and the spiking comes down, and therefore, we can quantify the value of the chemical reaction time divided by the heat transfer time by these two non-dimensional parameters. And mind you, we come to the end of our discussions with this. We told that what we want in an explosion is the time for the chemical reactions must be very much smaller than Th, or rather we get the value of Tc by Th as equal to, let's put that down, Q divided by Cv into T infinity multiplied by Ea divided by R naught into T infinity. Therefore, if the chemical reaction time has to be much shorter than Th, because then only an explosion could occur, we say, well, this is the number. Well, this number must be a large number, because if this is a large number, I can get Tc by Th to be very much less. I want this to be the condition, and for this number to be large, well, I find Q by Cv into T infinity could be large. That means the amount of heat generation must be large. We also said Ea by R naught into T infinity must be large for spiking to take place. and therefore, for a chemical explosion to take place, you should have large activation energy giving rise to a huge spiking, and we must also have as much energy as possible to result in a large heat release. Well, this is about the theory of our explosions based on chemical reaction time and the heat transfer time, and therefore, what is the conclusion? The conclusion is, well, I should have large values of activation energy which gives spiking and a large heat release, but if my ambient temperature is smaller, I am better off because I can get better spiking and more heat release when the more heat release non-dimensional term when my T ambient is smaller. In the next class, what we do is we follow this up. We will take a look at the formation of chain carriers during the induction time, and we will interpret one or two explosions. Well, thank you.